All right, so let's take a look at this next problem. So this one is an open box top, and so hopefully you guys have seen this before. And if you have not, again, it's great. We'll actually talk about this. But an open box top is to be made from a rectangular piece of card stock, 8.5 by 11, 8.5 inches wide and 11 inches tall. By cutting, in other words, that's an actual regular piece of paper. 8.5 by 11 piece of paper is a regular piece of paper. All right, by cutting out squares of equal size from the four corners and bending up the sides, find the maximum volume for the box can have, and what size squares should be cut to create the box of maximum volume. All right, so this is the regular 8.5 by 11 sheet of paper. So with that, it's supposed to be cardstock, but it's okay. This will work. So with that, we are going to cut out pieces from the sides here. And they're supposed to be squares, but this, just to let you know, this will not be squares. I cannot draw that out perfectly. So with that, this is what we're talking about. Now, with each one of these pieces here, each one of these angles right here, or each one of these pieces are supposed to be the same size. So with that, looking at this big part down here, this is actually 11 inches. This is normally 11 inches down here. But with that, we have these pieces right here that, again, are the exact same size. We're going to say those are X because we don't know what that length is yet, but they're the exact same in all four corners. So we don't know what that is. But if we look at it here, whatever is left over is what we actually have for our box. So if you take a look at it here, this is actually going to be 11 inches minus the two X's that we have right here. Same thing's going to happen up here at the top. This is 11 inches minus the 2X, the two X's that we have here that we're going to cut and bend up. Now on the sides here, this is 8.5 right here. So from this end to that end is 8.5. And again, we're taking two pieces of it and we're going to bend it up. So it means here, this technically is 8.5 by minus 8.5 minus 2X. Same thing happens here. This is 8.5 minus 2X. Okay, so with that, let's go ahead and cut it real quick so you guys can see it, and then we'll actually take a look at this bad boy. Let me do it on this. And again, this will not be accurate because I didn't draw these out accurately. Do this really quick. I'm trying to get this done quickly. It's okay. All right, so with this, we're going to bend these up here. And so here, this is the 8.5 by 11. That's minus 8.5 minus the two X's. Make a box here. We'll bend these up too. We'll bend this up here. All right, so we're going to, so in other words, we just bend it up, all of them there. And what we're going to do is we're going to actually bring this up so it makes an actual top, box top. That's not that bad. That looks good. We're going to bring this up. That one's not as good. That side was bad. All right, so we have a 3D box, in other words. And let me actually pull this inside, so you can kind of see too. So here, if you look at it, we have our 3D box. Again, a 3D box going on here. And so with it, if we're talking about our length times our width times our height, because we're talking about volume, our length here is 11 minus 2x. So that part right there is 11 minus 2x. It's our length. Our width, which is this part going this way, is 8.5 minus 2x. And our height, how tall the box is, because again, this is the same sides, that should be x. So I'm going to go back to the smartboard lesson, and we're going to talk about, again, using 11.5 by 11 minus 2x, 8.5 by 8.5 minus 2x, and then x. So we're going to do that part. So let's go back there. All right, so we just talked about making the box here, and so we have the box, and we're labeling it here. Again, that's step 1. So with that, step 2 says that we're going to go ahead and make the formula, optimize the formula, because it says what is the maximum volume? The maximum volume. So it means we're doing with the volume when it comes to our equation. And the volume of a cube or rectangular cube or whatever, prism, length is length times width times height. Let me put dots there so it doesn't confuse anybody. Length times width times height. So with this, we already know this is our length right here. This is our width. And this is the height of the box, how high it goes up, because we cut it and we flipped it up. All right, so here, this is going to be 11 minus 2x times 8.5 minus 2x times x. And that's going to take our volume. All right, so you can multiply that out if you want to, but again, we're going to put that directly into Desmos and actually graph it out that way because it makes it easier to deal with. So with that, we're not going to multiply that out, just in case we multiply it out and we multiply it out incorrectly. All right, so the third step again says to make sure that anything is multiple variables. In other words, if it's something other than just x in a problem, that means we have to do something else. The great thing about this is everything's dealing with x, so we're good. So that third step is done. We don't have to worry about that. So now the fourth step is now where we have to find our max and then be able to tell like what is the actual, let's see, do they want to know the dimensions or do they want to know the actual, I think they want to know the actual dimensions. So it says find the maximum value of that the box can have. So the max volume itself. And then what size squares should be created from the box. So it means we need to find two answers. What is the actual maximum volume there? And then what is the actual size of that square? So in other words, the x portion. All right, so here, let's go ahead and go there. Let's go to Desmos, and then we'll come back and actually write the answer down. So we put the equation into Desmos, and we have this wonderful graph here. So with that, we need to find the maximum point. And if you look at it really quick, and let's get you out the way. If you look at it really quick, you know, okay, it goes up forever, it goes down forever. So technically, those are not our max or mins because we don't know where they stop. So let's zoom in a little bit. Let's pull in what we do know. So at this point, we have our relative max and mins. And so here, we know at that point, this is our max, at the highest point it will go there for relative. All right, so with that, we'll go ahead and say, at this point, that's our max. So our x value should be that part right there. And again, we're trying to find out what x is. So that actually says what is the size of the square? And this x, what's the square? So x, we can say approximately, or you can say is equal to 1.585. And we don't have centimeters or anything of that sort here. Oh, we do have inches. So this would be inches. All right. And then it says, what is the max volume then? So find the volume, the max value, or max volume that a box can have. And that max volume is this part right here. Because we said we found the equation right here for our max volume. So that's a max volume equation. And so whatever is the maximum point on there, that's the part that actually tells us what the maximum volume is. So at this point, the maximum point is right here. Our x value is that. That's the parts that come in here and that in the equation itself. But the volume portion right here, it should be the output, the y value, the outputs here. So your max volume is, let's say, we're going to round it. We'll say about 66 inches cubed. So we rounded it, but 66 inches cubed. And that's it. That's how we maximize what's going on. Maximize the volume.